Hello. In this video, I'm going to be working on the problem in Quiz 4 where we discuss, where we find how fast the distance between two objects is increasing over the interval of 3 seconds. So in this case, the problem says that there is a balloon that is rising at a constant rate of 5 feet per second. We'll go ahead and write that down now. It's always important to keep track of your work. Okay, so the balloon is rising upwards at a constant rate of 5 feet per second. The other piece of information we were given is that there is a child on a bicycle who is riding along a straight road going at a constant rate of 15 feet per second. Now I'm going to write that down. I'll explain why I'm doing it this way in just a second. 15 feet per second. All right. And then it says that when he is underneath the balloon, directly underneath the balloon is 45 feet high. So I'm going to write that down. And zeros here. So what we have to do is, according to the question, is how fast is the distance between the boy and the balloon increasing 3 seconds later? So for this problem, what we're going to want to find is a differential, or the rate of increase of the distance between these two objects. So for this, we're going to need a couple of rudimentary problems from you must have learned in trig or earlier. Now the first one is Pythagorean theorem, which is a squared plus b squared equals c squared. So what we want is, we're given two different rates, and we're given 2 different points. So the boy would be at point 0, 0 if you were thinking about this on a coordinate plane. And the original point for the balloon would be at 45 feet. It would be right around here. So what I want to do is I want to find the distance first between these two after 3 seconds. And more importantly, the final question I want for this part is I want to find the rate. So to do that, I'm going to have to find the differential equation for the Pythagorean theorem, which I'm going to explain right now. So for that, you're going to want to go ahead and bring down the 2 power from each of the sides, including on both sides of the equal. So you bring down the 2 in front of the a, and then you're going to want to multiply that a by the differential rate for that side. And you're going to want to do that again for b too. So you bring down that b dt equal to 2c over multiplied by its rate. Okay, so now you see that once we brought down the powers, we can go ahead and eliminate the 2's and simplify it. No need to make it any more complicated than it is. So that will give you a times its derivative plus b times its derivative is equal to c times its derivative. Now for this part, you're going to want to use your algebra skills to go ahead and isolate this rate on its own. So we're going to do that by multiplying out this c. So what we're going to get is 1 over c multiplied by this side right here. So it's going to be a times its speed, or its rate that it's going, and then plus b times its rate that it's going, and that is what's going to get us our final answer to find the rate of increase between these two objects over that 3-second interval. Okay, so right now we have a few different variables here. We are already given the rates for a and b, so that's the 15 feet per second and the 5 feet per second. And what we're going to want to do is we're going to want to find the lengths of their sides now, based off of after 3 seconds, which is the end of the interval, which I'm going to actually go ahead and mark out here. 0, 3, and I'll explain that later when we get into the second part of the problem, where we go ahead and find the absolute max and min of this function. Okay, but for right now, what we're going to do is we're going to go ahead and find what these are equal to. So we're given a rate and we're given a time, which means with those 2 pieces of information we can find what the distance is. Okay, so for the first one, we're going to go ahead and solve for the balloon after 3 seconds. All right, so we start out with an initial height of 45 seconds. That's where b is starting out on this interval of 0 to 3, is at 45 seconds. So whatever we find for the rate, we're going to have to make sure to add that height in there. So it's going to be 45 plus 5 feet per second multiplied by the number of seconds that we're going towards, which is 3, which will give you a total of 60 feet. And then for part B, we don't have, our original height is 0, so we don't have to add anything to that at all. We're just going to take 15 feet per second. 15. We're going to multiply that by 3, that gives us 3 seconds. And that's going to give us 45 feet, and where the bike is, and its position on the x coordinate, after 3 seconds. Alright, so now we have an A and we have a B. We're going to go ahead and we're going to plug back into this original theorem right here to solve for the hypotenuse. So that's going to be square root of 45 squared plus 60 squared, which, if my math is correct, I believe equals out to approximately 75 feet. So I'm going to go ahead and mark this on my other triangle here. It's always good to keep in proper notation what you're doing. So for the A, that's going to be 60 feet. That's going to be 75 feet. And then this right here is going to be 45 feet below on the bottom. All right, so now we have A, we have B and C, and we are given the rates for A and B. All we have left to do now is to plug back into this original formula that we found right here. So that's exactly what I'm going to do over here on this board. I'm going to go ahead and erase some of this bottom work over here. So that is going to be 1 over 75 times A, which we found earlier is 60, times its rate, which is 5, plus 45, which is B, times its rate, which is 15, and all that is going to give us how fast or how much it's increasing over that 3 seconds. So I'm going to go, I've gone ahead and I've already solved this ahead of time. It's going to be equal to 13 feet per second. And what that answer means is that at the 3 second interval, in this interval of 0 to 3, at the 3 second mark, the object is the balloon and the other object, the child on the bike, are moving away from each other at 13 feet per second. And now, what's going to help us think this through is we're going to go ahead and graph this information now. Okay, so for this problem on quiz 4, I'm going to be solving the linear approximation problem. We're given an f of x function of the square root of x plus 3, and we're given a point A equal to 1, and we're given these two values, the square root of 3.98 and the square root of 4.05. And they want us to find the approximate value of these 2 points with this information. So I guess the first thing we have to start out with is explaining what linear approximation is. So what we're going to do is, first off, we're going to graph this function right here, square root of x plus 3. As you can see over here, I have it already set out. This is the original function right here. It starts out at -3, because that's where the point would start. And then like most, or like all of the square root functions, it's going to curve out like this. I have this 1 right here on the x-axis, which is where the A is. And I'm going to explain why I have 2 here in just a second. So we're given this point A is equal to 1. So I'm going to plug that into this function right here. Root 1 plus 3, which is obviously 2, because it's going to be 4. So that's why I got 2 here. Now the reason I have the second line, the second linear line that's going straight here, is the point I'm getting to with linear approximation. So the reason we do linear approximation is because f of x is approximately equal to L of x. What I mean by that is that we can take a tangent line and a point that intercepts on this function, in this case the square root of x plus 3. It's going to be at the 1 point at A, and we're going to try to find the slope of this line right here, because at this point right here, the slope of this linear L of x and the slope of this f of x are equal. And we can use that slope to find the approximate values of those other values. So I'm going to get started with finding the derivative of this function right here. So derivative square root of x plus 3. I'm just going to make that x plus 3 1/2 just to make it easier to solve the derivative, obviously. So it's going to be equal to 1 over 2 square root of x plus 3. And I'm going to go ahead and plug in 1 to that to find the slope of that point. So f of prime of 1 is equal to 1 over 2 square root of 1 plus 3, which is equal to 1/4. So f of a, or f of 1 in this case, is equal to 1/4. So what the heck are we going to do with that? Well, as you can see here, I have some preliminary notes that have already been written up here. L of x is approximately equal to f of a plus f prime of a multiplied by x minus a. So what we are going to do is we're going to take our original f of a, so f of 1 in this case, I should probably change that. F of 1, so that's going to be 2. Lx is equal to 2 plus 1 over 4, taking the slope of that, x minus 1. So we're going to go ahead and simplify that out, and we get x over 4 and plus 7 over 4. So that's the linear approximation equation that we just found right there. So what we're going to do with that is we're going to find the approximate functions of this. So 3.98. What we are going to do is we're going to take, we have x plus 3 here, okay? Square root of x plus 3. So in order to get 3.9, x is going to be equal to 0.98. So what we're going to do now is we're going to plug that into this formula here. So L of x is equal to 0.98 over 4 plus 7 over 4. And I'm going to double check because you're going to want to plug that into your calculator. And you're going to get an approximation 1.995. Now what does that mean? So basically what we did was we used the slope from the from this tangent line right here, this tangent point that it hit, and we went backwards to try to find what approximately the square root of 3.98, what the value would be. So as we can see here, when a is equal to 1, the value is 2. But on the slope right here, when 3.98 is what the value is, it's going to be just below 2 at approximately 1.995, and that checks out. So the next step we're going to be doing is we're going to do the exact same thing, but we're going to do it for 4.05. So L of x is equal to the square root x plus 3. So in order to get the square root of 4.05, x is going to have to equal to 1.05. And then again, we plug that into the linear approximation formula. 1.05 over 4 plus 7 over 4. And again, I'm going to check my notes just to figure out what that is. 2.0125. So again, by being able to figure out the slope of this tangent line, we could approximate a value for those on the curve. And that's that.